Hello and welcome to another video on machine learning in biotechnology. I'm Ian Hoffecker, and this video is going to be about statistical models and the maximum likelihood estimation method. So we begin the discussion here with summary statistics. So most of you are familiar with things like the mean, the variance, standard deviation, things that we use to describe our data with one or two numbers. So the mean is going to give us an idea of where our distribution, our data is centered, and the variance and standard deviation are supposed to give us an idea of the spread of that data. But at the end of the day, these summary statistics are quite limited. And so if we look at this picture here, so in fact, all of these images have the same mean and standard deviation. And obviously, if we visually inspect the content, we can see how the data is quite different from one data set to another. So the mean and standard deviation, mean and variance here, are failing to capture structure in this data in a way that tells the whole story. So this brings us to the idea of parameter estimation and fitting of specific distributions to data. So the mean and especially sample mean and sample standard deviation, we can fetch these for any data set at all, no matter how it's distributed. But what we would like to do is have a theory of the probability distribution underlying our data that's generating the data. And what we would like to do is fit that distribution to the data that we see. And so these probability distributions, whether it's the normal distribution or the binomial distribution or the Poisson distribution, so forth. So they have a particular shape, which is determined by the parameters that we feed in. And if we think that the generating process behind our data happens to agree with the probability distribution, then it's simply a matter of picking the right parameters to fit that distribution to our data. And then we have a theory, an explanation of how that data was generated. And we can even use this to predict or generate new simulated data, and have a more complete scientific picture of our problem. So this is the format, right? We have data going in, and we want to get parameters out. And so another way to write this is we're trying to find the argmin of some loss function that we want to minimize that's going to give us an ideal set of parameters. And so a common method with its roots in classical statistics is the maximum likelihood estimation method, or MLE. And the idea here is that we're going to base everything on maximizing the probability that a particular set of parameters and distribution generated the data that we observe. So we have this conditional probability statement. So this is the probability P of observing the data given some set of parameters. And what we're trying to do is maximize this value. So we want the argmax, in other words, the arguments of theta that maximize this statement here. And so this is called the likelihood. So it's just this conditional probability here, but in the context of this problem, trying to find parameters, this is typically referred to as a likelihood. And again, we're searching for this perfect set or estimated ideal set of parameters. And so we can imagine this more visually here. So let's say we have a data point and we have a hypothetical distribution. Let's say it's the normal distribution here, Gaussian, and Gaussian takes some parameters, right? Mu, sigma squared, the mean and variance. And if we fiddle with these parameters, we can move this distribution around, right? And change its width. And some distributions, in other words, some parameters are going to be more or less likely to have generated our piece of data here. So we can see the distribution on the left, the probability associated with our point D here is quite low. And the probability, the height, in other words, of the curve in the second one is higher. So we might say that the likelihood is higher for the curve on the right here. And then once again, we can keep changing this. And so typically we have more than one data point. And what we want is a situation where we've satisfied the constraints that those multiple data points give us. So with one data point, it's kind of hard, right? We could center our distribution over one data point, but different spreads, we don't have any information about the spread. But in the case of multiple data points, we do. So this system is fully constrained. And what we want to do is maximize the likelihood that a particular distribution produced this data here. So we're looking for something like this guy here, which is kind of centered where our data is centered, and the spread makes sense as well. And the way we do this is by finding the product of all of these likelihoods for each data point. And so if we recall the rule of a joint probability, remember that if events are sampled independently, the probability of two of those events occurring in conjunction with one another, so A and B, is going to be the product, so multiplication of those two events. And so you can extend this, right? So it doesn't have to be just two things here. It can be, 100 or 1,000, and we're going to multiply them all together. So we multiply all the likelihoods, and this is going to give us a kind of net likelihood for this particular data set. So the big D here represents all the data, and then these X sub I represent individual data points for a given set of parameters. And so if we change the parameters, we'll also get a different value of the overall likelihood here. And so what we want to do is maximize this likelihood value. So we get this likelihood here from multiplying all these conditional probabilities. And then often this is done computationally. And so computers have an easier time working with sums than products or multiplication. So what is typically done is we take the log, and by taking the log, multiplication becomes addition. So this statement, instead of being the product of likelihoods, becomes the sum of log likelihoods. So this is just a computational trick. And then once again, going back to that statement, this optimization statement, so we don't just want one particular value here. What we want to do is change theta and tweak the knobs and find the best theta, the one that maximizes this statement here, that maximizes the sum of likelihoods, or the sum of log likelihoods. And then finally, another little piece is that due to historical reasons, there's a convention that you typically minimize things. So usually we're working with what's called a loss function or a cost function, and you want this to be low. So rather than maximizing the log likelihood, we'll be minimizing the negative log likelihood. And so all this is just a minus sign put out front. And then this is the optimization problem that we're addressing. So that's for one variable case, but so this is a very kind of general concept. So we'll see this, so we'll return to this idea with linear regression, but let's say we have, instead of just one X variable, we could have two variables, X and Y, and we have our data that's normally distributed for each given X value centered at a different Y point here. And so we can formulate this in the same way. We still want to maximize the likelihood in this case. So instead of the likelihood being defined as X given set of theta, it's Y given a set of theta and a particular X value here. So for each X value, we're trying to maximize the likelihood of a normal distribution distributed over some point here. So analytically, this optimization problem, this maximization problem, is a calculus problem. So if this is the function that we're trying to fit, and we move this around by changing our parameters, we'll be getting different values of likelihoods, or the different values of the negative log likelihood, and it will be changing at a particular rate depending on each step or change in the parameter that we take. And different changes or steps in the parameters we can think of as a small incremental change, like del mu here, or del sigma squared. And the point where you no longer see any change in the negative log likelihood, in other words, where the slope of the function is 0, that's going to correspond to some sort of minimum or maximum, if we remember back to calculus. So to get the maximum likelihood estimate from a known analytical probability distribution, we would simply take our expression for the Gaussian distribution, compute the negative log likelihood, and then compute these derivatives with respect to mu and sigma squared with respect to the parameters. And we could actually just solve then for these values analytically. But in practice, this is not done so often because typically analytical solutions are hard to get. And what we'll see in most cases is numerical optimization. So we won't actually spend too much time on this analytical approach, and we're going to think more about this numerical approach. And the idea here is that we're going to systematically explore the parameter space. So in this example here, I'm showing how for each value of sigma, so one of our parameters, we're sweeping through and testing different values of mu, different values of the mean. And these different values of the mean will change the individual contributions of each of these data points to the likelihood. So this is, you can see on the x-axis here, these are our individual data points. Depending on what sigma is, depending on what mu is, these guys will contribute some likelihood value. And what we're looking for is a value that gives a large likelihood value. And so you can see that this peak here, which is just plotting the overall, like the total net likelihood, it's different for different values. So here is a really high one. So this would probably be a good candidate. And here is a worse candidate. And we could see we would want to find the center of this thing, but also the value that is the value of sigma that's giving us the biggest height. And so that's kind of a brute force approach, but the computer is going to do more or less something like that, test many different values and evaluate them, and try to return the best set of parameters. So you can see here, just an example, this is trying to fit normal distribution to these 5 data points here. And we generated these data points with this particular mean. So this was the true parameter value. And then this is our likelihood function. And if we maximize it, in other words, we have this point here, we'll have an estimate then, which you can see is not exactly the same as the original, but it's close. And the more data you add, of course, the closer your estimates get. Yeah, and note here that it's asymmetric, right? So this likelihood function, it's not a normal distribution, right? It's a distribution that's, or it's a function that's defined by the spread of the data. And so if the data is not perfectly normally distributed, your likelihood function is not going to look, it's not going to be symmetric. And so here we have an exercise. And so this is a follow-up to the previous exercise where we generated random nucleotide sequences, or UMIs, and checked to see if they have the GGCC sequence in them, which would mean that they could get cut by a restriction enzyme. And if they can get cut 5 times, then we decided that this would be some sort of special threshold where something bad happens in the experiment. And so we're interested in how many UMIs do you need to sample? In other words, what is the number of trials you need to get to encounter 5 of these cut events, or 5 successes in the language of probability distributions. And what we want to do now is, let's say we're starting with the data. So we didn't generate it. Let's say that we've run an experiment and actually we have the data. So we're looking at a set of numbers of trials to 5 cuts. And we've hypothesized that the distribution here, so this is the negative binomial distribution function, or the Pascal distribution, it's called. So we have an analytical expression here, and we're proposing the hypothesis that this process explains the data that we have. And what we want to do is fit this distribution to our data by changing the parameters here. And so this distribution works more or less how we've set it up here. So there are a critical number R of success events. And so this gives you the probability for a given number, a certain number of trials, so how many trials it takes to get to R success events for a given probability of a success on any one event. So the two parameters in this case are the critical number and the probability for one trial. And then the random variable, the x variable here, or k here, is the number of trials. And so if we were to plot it, it would look like this, right? We have trials on the x-axis and probability on the y-axis. And if we were to change the R parameter here, we would see that this curve shifts. So a larger number of parameters kind of push the distribution to the right. And so we have certain spread of data, and what we want to do is fit this distribution. And so that's the task. And the way we can do this is by performing the maximum likelihood estimation method. So what we're going to do is make a function that computes the negative log likelihood for this distribution. So we have this distribution function in the code that I've set up here in the GitHub. You have already set up distribution function for this Pascal or negative binomial distribution. What we want to do is make a negative log likelihood function, and then that's going to be the loss function that is fed into our optimizer, which is also already set up. That's maximum likelihood estimation. And so to just kind of give a summary or overview, this topic, parameter estimation, this is a really important tool in scientific computing. So we have some data, it's been generated through an unconfirmed process, but we have a theory about what generating process may have produced it. And so what we're doing is we're fitting a model, we're proposing a model and fitting our data to that model and coming up with some parameters at the end that can allow us to generate more data, for example. And so this has a lot in common with the basic themes of machine learning. So maximum likelihood estimation is probably not considered machine learning by most definitions, but it ticks a lot of the boxes. We're approximating a function, we're working with data, we're finding parameters, and we're generating or have the opportunity using Monte Carlo to generate some output. This is a powerful technique. The last point here is just that, yeah, when we're fitting this data, we're not just thinking about the shape of the curve. So for example, Poisson distribution and binomial distribution, a lot of these curves have a similar kind of bell-shaped shape. But what we're after is an explanation of the underlying process. So if we successfully fit a distribution, then we're in a sense saying that we know something about the underlying physics that led to the data that we're looking at. So that's all for this video. Thank you very much, and I'll catch you in the next one.